Hi. Welcome to the progressive conversation where we demonstrate examples of how we can do distributed training on EKS anywhere on bare metal with our NVIDIA GPUs. In the previous example, we had actually showcased the TensorFlow and specifically the Kubeflow deployment of TF job and doing a data parallelism and actually doing a small benchmarking actually, right? Where we saw how we can do data parallel methods and actually aggregate, the computing power of multiple GPUs and accelerate our, training jobs as such, right? So while that said, data parallel in its own is a good way to actually approach distributed training. But given the recent trends around how the data itself, the data sets are exploding, plus the rise of the LLMs where the model sizes are also exploding, you often fall prey to a typical challenge where your one GPU cannot host the entire model, right? And that's where you feel constrained, as if you had a bigger GPU or you had something else as a magical wand, right? In this specific video, we will try to tackle this problem from two perspectives. Okay, we will take an example of distributed training with a llama LLM, llama 2. Although it's not a very small, it's not a very big one, it's a 7 billion parameter, but we would actually showcase this as an example to demonstrate how the constraints are presented and then what we can do in the context of distributed training, especially taking model parallelism and blending it with data parallelism. Okay, so I'll talk a little bit more about this. The example that we will be doing is with again Kubeflow and PyTorch job. So we will actually move away from TensorFlow Keras to a PyTorch conversation. The CRD that is actually given by Kubeflow is called as a PyTorch job. Like a TF job for TensorFlow, you have a PyTorch job. Okay, so we will be using that CRD to orchestrate our distributed training actually. So what are we going to train? We are going to train a Hugging Face format model for llama 2, a 7 billion parameter model. And in doing so, we, and I'll show you it in the lab, when I started training, so I have two EKS anywhere bare metal nodes at my disposal, okay, each with two L40S GPUs, right? So that's a total of 4 GPUs. But being L40S and I think 48 GB of approximately memory, I found a constraint where when we started doing a fine tuning of this model, given a certain batch size and parameters and all that, let me show it to you where the error occurred, right? And this error is very important. We understood. You can see this one node with one GPU for a 7B llama 2 model. And this is typical, right? I mean, your use case could be different. Your model could be different. The kind of GPU that you have is different. But at some point, you will feel this kind of constraint presented where the model simply doesn't fit into model and all the other requirements which actually fill up the tank of your GPU don't fit into a single GPU, right? And that's where the challenge occurs, where you have a CUDA out of memory error and things like that, right? Now, while I won't go into the detail, this was done with one node and one GPU, okay? Now, the challenge is that you can optimize a certain thing. You can reduce the batch size and things like that, right? You can optimize many things, but still, if you do come across the upper limit and an upper ceiling where everything optimized, you still are not able to fit everything into a single GPU. That's where you look at, for example, model parallelism. And in the context of PyTorch, they have something called as FSDP, which is a fully sharded data parallelism. It's actually a blend of sharding both the model and the data. So it's an optimized take on model plus data parallelism. And I think it's a worth example citing and validating here. Again, I'm not going to go through there's enough knowledge on the internet of what it is and things like that. But PyTorch FSDB, FSDP can kind of gives you the edge in terms of trying to move out of this very inconvenient situation. Let's say that, right? So let's see what we are going to do. Okay. We're gonna, so this is a high level, schematic in terms of how this would operate. Okay, we will have our basically training job, okay, which will be split across multiple GPUs. Okay, and then the shards are basically of the model weights and everything. So the model is sharded across all of them, and whatever, the continuous training as it occurs on the epochs, everything kind of converges towards the end, right? uh, we are going to use the training operator. We have already, so our setup is continuing from the previous blog where we had done, the TensorFlow with Keras distributed training. So if you haven't seen that blog, please go through it. So I'm not going to cover the prerequisites in terms of the NVIDIA GPU operator deployment and training operator deployment, the Kubeflow deployment, all that is covered there. We will focus on this piece here. So we will deploy an etcd pod, okay? And this kind of helps converge the state onto all the replicas of a particular training job, okay? And these you can consider as the replica of your training job. And in this case, we are going to fine tune our Llama 2 model, right? So we will start by deploying, and I'm going to straight away, take out some, this is a nice example from, AWS, but it's highly tuned now or corrected, let's say, for EKS Anywhere deployment. The default doesn't work. I had to kind of, work up a little bit of the code base and things like that. So anyway, that's okay. So we will use this manifest to deploy the etcd, okay, pod. And after that, we are going to actually export a few variables, including the Hugging Face token, because the Hugging Face token will give you access to downloading the Llama models that you would be using in your specific use case. In this use case, the model is Meta Llama, Llama 2B, okay, 2 Llama 2 and 7 billion. We have to specify the rendezvous host and the rendezvous port. This is where the entire convergence of things happen here and the synchronization goes on. We also have to specify the number of workers and the GPU per worker, right? Because we are going to distribute across a certain capacity base, right? In that case. Plus, I'm exporting a CMD. That's where, we will pass it as a variable when we start the job with the Hugging Face CLI login, the token, and then running the torch run command, with per node, how many processes will be invoked. So that's equal to the GPU per worker. And then how many nodes are we actually presenting in the entire affair. So that's the number of nodes, the number of, workers. Plus we are actually fetching, scroll down, this is a little inconvenient. Okay, so, and plus we are downloading actually from, Llama recipes, a fine tuning, method. And we will run it for, 3 epochs. The batch size is going to be 3. Enable FSDP. This is what is important. And then the model name and the output directory. Obviously, you can go ahead, pass in a few more arguments and things like that to actually make your whole thing more optimal. But this is what we are going to do actually, right? Now, once we do that, okay, there's another thing. So this is just passing in the variables. We do have to create a Docker file or a Docker image that will be presented to our training job, right? So we, in my case, I'm running a CUDA 12. Okay, so my base image is going to be PyTorch CUDA 12.4 with cuDNN 9 runtime. And then we clone this particular branch from the last Llama recipes. Okay, so the branch is called as AWS do FSDP. Then install some of the things here. You can see till the point. Yeah, so this is what will be required actually for us to, build our Docker image. Now, this is going to be a massive Docker image. I think about, I'm not sure, but about 11 GB or maybe, yeah, something like that. Okay, so it's going to take a lot of time actually to build this Docker image. For me, the Docker image is already built and pushed on to my Docker Hub. Okay, so I have already built this for convenience. I've provided the commands. So you need to push it to a valid, either a private or a public repository, whichever ways you look at it, right? If it's public, then it's okay. If it's private, then you have to supply when you download a secret as well, right? In this case, I've just pushed it as a public repository. Now, once our Docker image is built, we will create a file called as fscp or YAML, which basically is defining a custom resource of the type PyTorch job, like a TF job. This is a PyTorch job and the job name. And then we are also working with an elastic policy. Now you can, do an auto scaling also of the number of nodes and the replica count and all that. So you have at your disposal, the way to actually do min replicas, max replicas, and things like that. Max restarts is if there are issues, what happens, it will not time out and it'll keep retrying for those many instances, all these things. And then we specify, the replicas to start with or to state. So replicas is equal to the number of workers that we specify in our variables. Other things are okay. So on which nodes will this be deployed? So our nodes are labeled with, this particular label, GPU type L40S. And then the containers, so the image that you just built will be actually pulled in, okay? And then how many GPUs do you want to kind of work with actually, right? So the requests for the GPU. Some of the other thing, it's important to actually pass this variable, which I didn't see in the official example. Otherwise, there are some errors popping up. So the CUDA visible devices as a environmental variable. So 0 and 1 in this case, I have 2 on each node, right? And then the CMD that was actually passed as a variable up there to do a torch run. This one, that's what will invoke the training job or the process. That's passed as a command, and then that's pretty much it actually, right? So let's go through this as an example. Okay, let me take this whole piece of the code here. I'm going to do a few edits to suit my requirement. Let's take this. Okay. Okay. Oops. Always a problem copying and pasting. Yeah. Okay. Okay, now I've already highlighted the problem, so I'm not going to do a one node, one GPU case because the problem already exists. So what we will do is we will actually change our number of workers to 2. So let's do this part. Min replicas is 2 and max replicas is 2. Okay. Other than that, I've already built my Docker image, so I'm going to skip this part of the whole Docker file and everything else. So number of workers 2, GPU is 2 per worker. This is okay. In the case of the EKS example, you have an EFA and DLC and all that. In the on-prem side of the world, I don't have any EFA and all that, so I'm just going to keep EFA per worker as 0. Yeah, so pretty much I think we are all set. Let me just, the other thing, yeah, so the rendezvous ID, just make sure that if you are redeploying the job, this needs to be changed. This value needs to be changed. It can start from 0 and then go on to whatever, right? So we'll keep it as 1 for now. If I redeploy the job, once it's completed, the job has to be deleted. And then, this rendezvous ID has to be changed actually. Okay, so pretty much this is about it before I start deploying. NVIDIA GPU was 2. Okay, good. Let me take this whole thing and let me paste it onto my terminal. Okay. Okay, so I do have the fstp.yaml. Let's just cat this. Just more to verify if the variables have popped in into that YAML file or not. Okay, so yes. Okay, so everything is set. Good. So if I say now kubectl get pods, you will see that there is no pod as of now. So we will start by deploying the etcd pod here. Copy that command. So let's take the etcd pod deployment YAML and let's deploy that first. Okay, so that's the starting point here. Okay, so kubectl get pods. Okay, so the pod is running already. Good. The next thing that I will be doing is to let's apply the kubectl apply. Okay, so let's just verify my GPU pods are running or not. The operator, yeah, so they're all good. Kubectl apply -f fstp.yaml. Okay, so you can see that if I say kubectl get PyTorch job, so the job is created. On account of this job, there will be, okay, so I think I passed in a wrong image. I did not pass in the right variables. Let me first kubectl delete PyTorch job fstp. Okay. And I'll tell you where the problem was because I didn't export the right tag actually, because the tag I've been working with is slightly different tab. So what I'll do here is, yeah, so this tag I will change. The last version that I worked with was 2.4. Okay, so let's take this particular thing. Okay, let me just verify if tag is indeed correct, because that's making because I've done a lot of experiments. So somewhere something I just need to make sure that that tag is correct. Okay. Okay. Yeah. So let's reapply that particular YAML. kubectl apply -f stp.yaml. kubectl get pods. Oh, sorry about that. I think I need to just really validate what's the tag here. And this happens. This is a good thing because this is a live demo. I don't want to kind of edit these videos to kind of show something that is not materialized rightly, right? No edits here actually, right? So nano fsdp.yaml. Did I make a mistake? Let's just see. Okay. Docker images. What do I have? Okay, so yeah, this is the one actually. Sorry about that. In order to accommodate, the actual command into a variable for, consumption by others, I had actually done some change of variables. While initially I was building the image, it came up like this. I had actually marked it like this, right? So that's okay. So let me just change this. Take this value. These are all good things to occur. It's all going to be authentic. Okay. That should be it. This is the one that I had last pushed. So kubectl get pods, no pods running, kubectl apply -f fstp.yaml. kubectl get pods. Now there is no error in terms of the image pull. The image itself will take, it's a big image. And if I look at kubectl get pods -o wide, should tell you that one of the pod is coming up on worker 0 and the other pod is coming up on worker 1. Okay. So since this is, this image will take a little bit of time to download, let me come back once the pod is created. Okay, so we can see after a while, the pods have come into running now. Okay. Now, they are in a running status, not a completed status right now, which means that the training should have started. And if, hopefully there is no error and things like that, if there are no challenges, then we will get to a point where the training epochs should also start. Okay. So let's just observe that. Okay. QCTL. Logs. Let's look at the logs from worker 0. Okay, so let's see what it's trying to do here. Okay, let's start from here. So you can see that the elastic operator has started with this config, and this is what we actually provided with all the the args as such, right? And the rendezvous endpoint and things like that. Now the etcd is running in the same namespace, right? So you don't have to provide the extension. So the service name and the port number should suffice actually, because these pods and the etcd pod is all running in the same Kubernetes namespace, right? So this is good. Okay, so you can also see here that between the both of them, one of them has been identified as the worker. So the worker 1 is what is actually acting as the master, and the other one is acting like a part of the cluster as such, right? The PyTorch, the FSDB cluster. Again, you will have to go through a little bit of theoretical knowledge in terms of what's the relevance of a global rank, a local rank, and things like that. How does actually, the whole, if you're interested, there are some very good videos in terms of how the whole forward and backward propagation and the weight of parameter updates and those kind of things are done in this FSDP construct. Again, feel free to kind of browse any amount of knowledge present on YouTube and other sites actually, right? Okay, so this is done. Let's not worry about some of these warnings. So we can see that, if, in the fine-tuning.py, there is a call out for clearing all the GPU cache. So this is good. Let's look at the worker 1 logs. And so this will go on for almost 5 minutes and all. Consider it as a part of the warm-up phase, let's say that, before the actual epoch start. So I'll pause, and once things progress, I'll just resume then. Okay, I'm back after a quick coffee, and I can now see the training epochs have started. The first epoch 1 of 3 is going on, which is good. We've not errored out at any stage saying that, this is a good start. Let's just observe what's happening. Let's get the logs. Hey, so if we scroll up, and I did mention to a point where our GPU cache was being cleared. After that, the shards were being downloaded. Okay, the shards got downloaded, checkpoints are loaded, which is good, right? I mean, and this is where the model also has been downloaded. You can see this one is Llama 2 7B HF, indicating this is so many 7 billion almost parameters, B float 16, mixed precision. Okay, so everything else is done, pre-processing, and the training epoch 1 started with 0%. You can ignore this particular one of the errors. It's a warning of sorts. Yeah, this one. This one particularly pops in my case. That's okay. It's I've also mentioned it in the blog. You can ignore this error. Simply so says that it'll load up the internal one. Okay. So we can see here the progress is now 30 out of 64 steps are completed for the first training epoch, right? Let's also validate the log on and you can see both the CUDA Dev 1 and 0, both are in use, meaning that this is worker 1. So both the GPUs are in use right now. Let's see worker 0. And worker 0 is also on training epoch 1. And yeah, all seems good here. CUDA Dev 0, CUDA Dev 1. So yeah, this will go on for a while. I think within may take about 20-25 minutes or half an hour. So I'll just pause the recording, and once the entire training is complete, we'll resume the recording. Still moving on, we can see now the training epoch 2 of 3 has started. The first epoch is completed with a perplexity score of 4.7. The loss is 1.5. The epoch time is 790, right? So we're done with the first epoch, 3 epochs. Let's just, let the things continue. So right now we are in the second. I'll resume when we move closer to the finish line. Okay, so there we have it. Our all the 3 training epochs have been completed. And then a summary report has been created here. Yeah, average training loss. So yeah, I mean, the point is that what we've done in this short demonstration, and let's also validate this on worker 0. Okay, yeah, so yeah, this also has completed its training epoch. So yeah, I mean, it's all done. Now, the point is that in this short video demonstration, what we've able to kind of highlight, the intent being when you don't have enough GPU, single GPU capacity to train, and now the result could be, or the driver's motivation could be a model being so large or combined with your data set, everything basically, your underlying single GPU capacity is not enough. Then you could look at a horizontal approach of involving multiple GPUs to split and shard your model, your weights, and everything else, so that you can, you can accommodate the entire enchilada of things into a single cluster. And the example that we've shown here is, with PyTorch FSTP, and where we have trained a Llama 2 7 billion parameter model, or not trained, or fine-tuned actually, and then being able to kind of, do this on a distributed basis actually. So I hope this kind of, I would say gives you some insight. Again, the intent of these blogs is to, one, articulate how this can be done, and second is most importantly how this can be done on EKS anywhere over bare metal clusters. Again, these are possibilities. You can do it on any other GPU clusters. So I hope you find this insightful. Thank you. Cheers.